Right. Hello, everybody. So today I'm going to talk about the work that I've been doing for the last year and a half, which is part of my dissertation. It's detecting a large population of subthreshold gamma ray pulsars using Fermi data. So this is in collaboration with my advisor, Tim Paglione, and Joshua Tan and Charles at LaGuardia Community College. So the motivation of this work, mainly we can figure out from this, that's not very smooth, diagram on the right. This is a diagram we're looking at that describes the spin down rate of the pulsar, which is at the y-axis, against the spin period of the pulsar, which is at the horizontal axis. So essentially, if we can measure both the quantities for a pulsar, we can plot them on the diagram, and we can also see that the gray dots are the pulsars that are identified across all of the wavelength, and the blue ones are the gamma ray detected pulsars using Fermi data. We can see that there's only a very small portion of pulsars so far detected in gamma rays. So coming back to the numbers, there's over 3,000 pulsars identified across the sky so far, and only less than 3,000 pulsars identified across the sky, and only less than 300 detected in gamma rays. So a little bit about pulsar emission is that they are powered by their spinning down, and the that loss of loss of the rotation energy actually is transferred mostly into the gamma ray emission, which is why studying the gamma ray emission from these objects are important. So for this work, I have chosen 527 high galactic latitude pulsars for this study from the ATNF pulsar catalog. And the reason for that is to avoid complicated background regions for gamma ray emissions. So, and a little bit more about the data is that I used the data from the Fermi Space Gamma Ray Telescope. It was launched in June of 2008, and I used the data from the instrument called the Large Area Telescope that has 2 steradian field of view, which covers 1/6 of the entire sky. And the instrument has been surveying the gamma ray sky nonstop from energy from 20 MeV to about 1 TeV. So there's a whole lot of data covering the entire sky for over 13 years now to make this population survey possible. And to analyze Fermi data, we need to use a maximum likelihood analysis to do that, because the large area telescope is similar to a particle detector instead of a conventional telescope. So I'm not going to get into all the details about the data analysis. If you're interested, you can come talk to me after the talk. And by doing the maximum likelihood analysis, we can obtain the test statistic, or the TS value, for the source that, or the object that we want to investigate. So I did that for all of the 527 pulsars that I just talked about. And then I used a stacking method by adding up all their TS values which is shown as the blue line over here. And I also did the exact same thing for 527 control fields randomly chosen as empty locations across the sky. And we can see that there is a significant difference between these two populations, which confirms there should be some signal that we're observing from this population of pulsars. And another piece of results I want to show is in this diagram, which we plot the gamma ray luminosity of the pulsars against their spin down power, which, if you remember from the first slide, they should be related, because we say the loss of the spin of the rotational energy of the pulsar is transitioned into their gamma ray luminosity mostly. And we can see that the blue dots, which are the Fermi pulsars, follow some empirical relations, which is either the gamma ray luminosity equal to the spin down power, or the gamma ray luminosity is proportional to the square root of spin down power. We also plotted the newly detected few pulsars, which are the black data points on here, and there's also about 40 subthreshold pulsars. So they are the signals are not quite significant enough to be classified as a detection. That's why they're called the subthreshold pulsars. And they also more or less follow these relations, which is another confirmation that we're seeing some signal here. Right, and that is all of my talk.
Yeah.
If we're seeing the L proportional to root E dot, can you give me a conceptual idea of what's happening to the rest of the energy?
Right, so there are other wavelength of emission as well, and we might also lose the energy into the pulsar wind nebula depending on the age of the pulsar. Yeah.
Other questions?
No.
Okay, if no questions, let's thank Yuzhe again. Okay, so our next speaker is Austin.
Hello. Okay. Hi, everyone. My name's Austin McDowell. I'm a PhD candidate at NYU. I worked with Andrew McFadgen on developing a model for learning about short gamma ray bursts through their afterglow light curves. So just real quick, short gamma ray bursts we know can be produced from the merger of binary neutron stars. And then the afterglow comes later when the merger remnant launches material into the surrounding medium. That material is often launched at relativistic speeds, and that accelerates electrons in the medium to helical motion, and that produces broadband synchrotron radiation, and that is the afterglow. So what we do, what our model consists of, is simulating the, if I can find this thing, here we go, simulating the outflow that produces the afterglow. So we run a bunch of hydrodynamics simulations, looking at different outflow geometries from kind of like a sphere, basically a spherical outflow to a more collimated kind of jet-like outflow. And then after we run these simulations, we calculate the synchrotron radiation that you would expect to see from them. And we create a very large table of spectral values that allow us to then kind of generate any arbitrary light curve for any model parameters that we want. So this is an example of that here. We have an afterglow light curve at 10 to the 17 hertz for kind of a more jet-like outflow. And we can look at what it would look like at several different observer angles. And these light curves we can create in a matter of milliseconds. So that allows us to do MCMC with a set of data. So that's kind of what's shown over here, and I'll blow this picture up in a second. But we can use MCMC to find the best fit for our data and kind of constrain the model parameters. And some of those parameters are things like the energy of the gamma ray burst, the density of the surrounding medium, and also like the angle that we're seeing this thing at. Okay, so here are a couple hydro simulations. Everyone loves a good hydro movie. So, you know, we have down here, this is kind of a more spherical outflow, and then you can see they get more and more collimated as we increase these two hydrodynamics variables, eta naught and gamma b. So I'll just let these play maybe one more time. So yeah, we do 334 of these exactly, and then calculate the radiation from each of them. So this is what it kind of looks like in the end. This is applied to the afterglow data of the gravitational wave event 170817, merger of two neutron stars. So these points, there it is. These points here are the individual observations, and then we do broadband fits to the data with our model and produce these posteriors for model parameters. So yeah, that's kind of what it looks like in practice, and you can apply this to any afterglow data, and that's the intention, is to get more afterglow data. We can look at more of these. Yeah, that's it. Thanks.
Thanks. Any questions? Okay, go
Sorry, I was just going to ask, what are those parameters physically?
Which ones?
Actually, all of them. I'm not familiar
sure.
with this particular.
So I guess I'll start with the. So in total, the model has like 8 different knobs that we can turn. Things like energy of the jet, like I said, the density of the surrounding medium. There's like the fraction of energy that goes into the electrons, fraction of energy that goes into the magnetic field, stuff like that. The best way to think of the hydro parameters. So this model is kind of a what I'm looking for. It's like first principles motivated. You basically just take a ball and deposit some amount of energy into it, and then it expands in its own rest frame. So eta naught is the energy in the rest frame of the outflow, and then you boost it with a factor of gamma b, and that creates a more jet-like outflow. Yeah, there's a couple more that go into it. But yeah, and then P is the electron distribution index, power law index. Yeah, does that answer? All right, cool.
Okay, another question there.
How much difference would it make if you used a more structured external medium? You know, there's stellar physics, there's stellar outflows, and so forth.
Yeah, right now we're just doing expansions into a constant density medium, but that's the plan going forward, is to run these simulations into like a wind medium, and then produce another spectral table that we can use for long gamma ray bursts.
Cool.
Thanks.
One last question.
Another one?
So you said you could apply this to any GLB. What sort of size data set and is there? Are you going to be looking at these individually, or can you say something statistical about the population?
Yeah, right now we're just looking at individually, but we want to make statements about like the population eventually. Yeah.
Number on that? I just don't know this field.
I'm not sure.
Okay, I think we need to move on.
Sure.
Yeah, let's thank Austin again. Okay, our next speaker is Ryan.
All right. Hello, I'm Ryan Golantz. I'm a second-year PhD student at Columbia University. And for the past year, Lorenzo Cerrone and I have been trying to understand how magnetic fields grow and decay in gamma ray burst afterglows. So gamma ray bursts, or GRBs, are typically divided into 2 phases of emission. There's the prompt emission, and then there's the afterglow emission. Both are powered by this relativistic jet that emerges from some central engine. So dissipation within the jet gives rise to the prompt emission, which is the initial burst of gamma rays that gives gamma ray bursts their name. But then the jet also launches this strong relativistic shock into the surrounding medium. And the gyration of charged particles in the post-shock magnetic field gives rise to this afterglow emission. So understanding this afterglow emission is really key to understanding the structure and propagation of relativistic shocks. But unfortunately, the details of the growth, the decay, the structure of these post-shock magnetic fields have eluded astrophysicists for many years. Observations of afterglows show that we need synchrotron radiation across a spatial scale of about 10 to the 12 kilometers. That implies that these magnetic fields are somehow amplified or stretched to extremely long coherence lengths. And it's a mystery, or maybe up until now, it's a mystery, how these magnetic fields arose, how they got to such long coherence lengths. So a key ingredient that a lot of models of GRBs are missing is the fact that actually in the early afterglow stage, some prompt photons stream ahead of the relativistic shock. And there in the upstream of the shock, they seed this circumburst medium with electron-positron pairs through pair production. So we end up with this beam of streaming electron-positron pairs ahead of the shock. And so when we have a stream of charged particles, like these electron-positron pairs, moving with respect to a charge-neutral background plasma, like the electron-proton plasma in the ISM, and then we get a beam plasma system ahead of the relativistic shock. And this system is shockingly unstable. That was the only pun I could think of for this presentation. If you can think of any more puns, I would love to hear them. I need more puns. But back to the science. Right, so the upstream, beam plasma system upstream of the shock is very unstable. And indeed, we see the signatures of the Weibull instability growing in the upstream region. So the Weibull instability sucks away free energy in the anisotropy of the beam plasma system and transfers this energy to the magnetic fields, effectively amplifying the magnetic fields from scratch. So we can see here in this plasma the signature current filament structures of the Weibull instability. On the right, we're looking along the length of these filaments. You see those long, elongated, thin, wavy structures. And on the left, we're looking down the current filaments, and we see these little pockets of underdensity carved out by the current filaments. So we know the Weibull instability is growing, but we have one problem. The magnetic fields amplified by the Weibull instability grow on the scale of the electron skin depth of the background plasma. So for the ISM, this is about a few kilometers. As I said earlier, to match it with observations, we need magnetic fields on the order of 10 to the 12 kilometers. So how are we going to bridge this 12 order of magnitude gap in coherence length? That's a real problem. But in our simulations, we believe the key is the continuous injection of electron-positron pairs into the upstream medium. We find that the longer we inject these pairs into the upstream medium, the lower the maximum magnetic energy in the upstream, but the slower the magnetic fields decay, as can be seen on the line plot to the left. And this is because as we continually inject more and more pairs into the upstream, we're continually feeding the Weibull instability. So the Weibull instability can then grow larger and larger scale magnetic structures. And so we know that larger scale fields decay slower than smaller scale fields. So we get these nice scaling relations for the mean wave number and the decay rate of magnetic fields in terms of this injection duration. And this will allow us to nicely extrapolate the results from our simulations to the properties of realistic gamma ray bursts. So in the spirit of Gotham Fest, I'll conclude with a slightly paraphrased quote from The Dark Knight that this continuous injection is the hero that the Weibull instability deserves, and it's the hero that GRB modeling needs right now. So thank you.
Thanks, Ryan. Any questions? Can I ask you a quick question? So in your simulation, what determines the largest scale the instability can grow to?
Yeah, the scale is largely controlled by this TF, the duration of injection. So yeah, that's the key parameter that changes the scale of the fields. Right. So naturally over time, the filament T structures of the Weibull instability will grow thicker. But we find that over the same time periods, with injection and without injection, or continuous injection without continuous injection, we naturally get larger and larger scale structures.
I see. So in a realistic medium, if there's already turbulence existing outside, would that affect how the field will grow?
That's a good question. So generally, the magnetic fields upstream of these shocks are very, very low. Like I think in the ISM, the fields are around microgauss strengths. So we don't expect there to be much turbulence already. So we're just taking the upstreams to be initially completely unmagnetized. In other environments, yeah, I think if we did have too strong magnetic field upstream, then we wouldn't get these Weibull mediated shocks. So I think then we'd have to investigate the different problem. And maybe model the shock differently.
Cool. Thanks. Any other question? Okay. If not, let's thank Ryan again. Thank you. Okay, so our next speaker is Katie.
Okay. Hello, everyone. I'm Katie Brevik. I am a postdoc here at the Flatiron Institute. And as expected, I see many, many new faces. So I'm going to just take this as an opportunity, even though I've been here at Flatiron for about a year, to introduce myself, hopefully convince people that what I do is quite fun and maybe you want to talk to me about it. Broadly speaking, I'm interested in binary star evolution. That's not really like a hot topic to a lot of people. It was in the 70s. But to get people excited, the way that I think about it is black holes. Everyone loves black holes. So we live in 2021. We have, where is it? Come on, 90 black holes. Holy moly, that's incredible. This beautiful manta ray shape of blue are all of these merging pairs of 90 black holes. Where do they come from? Nobody knows. Part of what I do and think about every day is trying to explain, at least partially, where some of these things come from. In general, my research identity is thinking about binary stars in a relatively cartoony fashion. And what I mean by that is I don't solve stellar structure equations in real time. Instead, I try to think of all of the ways that binary star interactions can shape binary systems at each of these different types of phases that we can observe. So if you start out as a star, you're starting out as a detached binary star, eventually a massive star will turn into a black hole. Your companion might start to accrete onto you, you become a close double compact object, and then eventually merge. In general, more advanced binary evolution leads to decreasing orbital size, and these orbital sizes, this is very bizarre, lead to differences in actually how you observe these types of systems. So in general, different orbital scales are observable with different observational techniques. I'm not an observer, I'm actually a theorist. So what I do is I develop this code, where is it? Cosmic. Cosmic is a binary population synthesis code, and what it does is it takes into account any and all assumptions that you could come up with to bring yourself from a zero-age main sequence star to a luminous star orbiting a compact object to an accreting system, double compact object, and merger. If you work on any of these types of surveys, there are binary stars in your surveys, I'd love to talk to you about them. As just a quick example of some of the things that I'm thinking about, this is some work that I've been working on with Adrian Price-Whalen and Nej Frankel, as well as David Hogg. And here we're considering two apogee candidates of a luminous red giant star orbiting a black hole candidate. On the first set of plots, I'm showing you the, luminous giant star mass versus metallicity. And then on the second set is luminous giant star mass versus black hole candidate mass. What we've done here is use Cosmic to simulate the apogee population of luminous stars orbiting black holes in Milky Way with a star formation history assigned by Nej, taking apogee data and giving all of our stars metallicities and ages. And then we use the Joker to decide which of these black hole plus bright star companion systems apogee should be able to observe. Our punchline here, actually, oh, one other thing that I should say is each of these, we run it for each of 3 models. This pointer is bonkers. And what matters for you is that each model has increasing natal kick strength when you form black holes. What that ends up doing basically is decreasing the number of black hole plus bright star companions as you increase in kick strength. That's because the kicks unbind the binary. And so what we're finding so far is that our apogee candidates tend to prefer 0 black hole kicks. We don't have enough to really say anything about kicks yet. There's 2, but SDSS 5 is coming online soon, and hopefully we will be able to say something better than just preference about black hole kicks. And that's it.
Thanks, Katie. Any questions? Okay, there.
Use your seat mic, please.
Oh, yes. I'll repeat the question. The question was, are we able to reproduce anything with the black hole spins in our binary population synthesis? The honest answer is absolutely not. We don't understand how black holes get spins. So anything that comes out of my cosmic simulations are totally ad hoc. Like I just put a spin on there, but it doesn't really mean anything physically. So I tend to kind of steer clear of that stuff because the stellar evolution theory just really isn't like at a place to say something useful there. Yeah, I wish we could though. That seems to be the best way to do it.
Cool. Any other questions? Oh, here.
Hi. I feel like this is the silliest question ever, but first of all, does a kick always unbind the binary?
No silly questions. 2. Natal kicks from core collapse supernovae unbind 90% of binaries.
Okay.
Yeah. So if we go, I wonder if I can go backwards. Let's try this. If we go to this phase, this is 10% in core collapse supernovae, and that's 1%. These mergers are like less than 0.01% of all binary stars.
I was wondering how you ended up with any binaries ever. So that it's a low percentage. Okay.
That's partially, I started doing gravitational wave things with these and was like, wow, this is terrible for binary evolution. So we're going to start looking.
Cool. Let's thank Katie again. Our next speaker is Christopher.
Okay, hello everyone. My name is Chris Teedy, and I'm a graduate student at NYU working with Andrew McFadgen. And I like to work on hydro simulations of binaries embedded in accretion disks. And I like to think about the dynamics of these problems as well as their implications for things like LISA and PTA sources, potential LIGO binaries and AGN disks, or even some stellar binaries. On the right here is some work I did during the quarantine phase of the pandemic, where we looked at the dependence of the binary migration rate on the prescribed thickness of your disk. And the motivation for this was primarily that historically in studying these, people had mostly looked at kind of warm, thick disks, kind of that Mach 10 case down there. And in that scenario, what you get actually is that the gas delivers angular momentum to the binary and actually drives it apart. So if we're thinking specifically about compact massive binaries and galactic nuclei, that could mean that gas is actually inhibiting a transition into a gravitational wave emitting phase and possibly even to merger. But for these compact binaries, if they have AGN-like disks around them, we actually expect them to be much colder and thinner from observations. And so what we did is we systematically raised the Mach number of our simulations. So we're considering colder, thinner disks. And we found that you actually get that the binary migration rate changes sign around Mach 25. So as you go to these colder, thinner disks, you actually kind of recover this picture of gas taking angular momentum from the binary, kind of shepherding it closer together, and possibly into a gravitational wave emitting regime where you could see it with things like LISA and PTAs. Something I've been thinking about more recently is more of a dynamics problem for this. And it's the question of how these binaries actually accrete. Because when people originally studied this problem in 1D axis symmetric cases, there was some thought that the centrifugal barrier from the binary might actually just prevent gas from making it onto the binary. And that could make it hard to see these kinds of things. But 2D simulations revealed that this is false. They do in fact accrete, and they do so at about the same rate as like a single black hole in an AGN disk or something. But this cavity structure it's complicated, and it's very nonlinear. And the actual process of mass transfer from the outer disk and the cavity onto the binary is not well understood. So in order to address this, I added tracer particles into our grid-based code that allow us to actually follow the histories of fluid elements as they move around in the disk. And these revealed a number of interesting things, but two of the kind of main things that we found about the accretion process are one, the presence of an accretion horizon, so essentially a point of no return, where when gas crosses it, it can no longer escape back out to the outer cavity and the outer disk. It necessarily will be swept up by the binary and will get accreted eventually. And then we also found that the actual mass transfer process from the outer disk onto the binary is dominated primarily by gravity. So if we look at the tracer particles as they're going around and from their phase space coordinates, we can actually integrate them forward. And by doing this, we found that almost all fluid elements that accreted became gravitationally predestined to do so about one binary orbit before they actually get pulled into a stream and deposited onto a mini disk. And you can kind of see it down there on the bottom right if you just consider like an n-body simulation of a bunch of concentric rings of particles, and you put them on initially Keplerian orbits with a binary going around, you actually find that you get these tidal deformations into streams that move them across the accretion horizon and even move material within like the Hill sphere of individual components. So what we found is that the mass transfer process is dominated by gravity, and then the role of the fluid dynamics in this problem is to remove angular momentum in the disk, to move material close enough to the binary to be kind of tidally captured by the binary, and then also in the mini disk to actually stop the ballistic trajectory of these streams through an accretion shock so that they stop, they join a mini disk, and then eventually get accreted by the binary. So maybe I'll stop there and take some questions.
Yeah.
Hi. So these are really exciting results. I think this is great work. Could you go back to your first slide? So that's right. So is there any kind of physical intuition you can help me with as to why the torque switch from positive to negative?
Yeah, definitely. So what we found is that if you look at the time average structure of the cavity, it actually has this kind of characteristic egg shape where the nearer sides are in quadrants that give you negative torques, and the farther sides are in quadrants that give you positive torques. And this kind of characteristic structure gives you a net negative torque on the binary, but it actually competes with positive torques from the mini disks. But as you consider colder, thinner disks, you're able to pack more material into the cavity edge and this kind of characteristic egg structure. And that changes this balance of positive negative torques and actually causes the negative torques to start winning the battle and driving the binary together. Does that answer your question?
Yes, very much so. Thank you.
These are super cool and hypnotic. I have a million questions. I'll talk to you about them later. But have you any plans on putting some of these in shearing flows? Maybe thinking about feedback, stuff like that.
Of the tracer particles?
No, the little black holes themselves, right? Just embed the whole thing in a shearing flow. You know, if you want to mock up a binary in an AGN disk, say, right? Embed, right? So put it in a shearing flow so it's faster on one side, slower on the other, put in some feedback, see what happens.
It's something we could definitely do, and we've thought about a little bit. There are tons of things that you can kind of pursue with this problem, but I would definitely be interested in it if you want to talk about it.
Totally. Yeah.
I think we need to move on. Let's. Okay. Next up is Barry.
Okay, cool. Thank you. All right. So speaking of things in disks, so I am a member of a large, friendly, collaborative New York City group that is interested in working on the problem of things in AGN disks. If you are interested in stellar mass black holes, intermediate mass black holes, supermassive black holes embedded in gas disks, we are interested in talking to you. Neutron stars, things exploding, weird stars, all kinds of exotica. Please come and talk to us. So I'm going to start with Astro Twitter, where all the cool kids are apparently these days. So, a big question that Katie pointed to is where are all of these black hole mergers that we're detecting in gravitational waves? Where are they coming from? All I'll say is that there are many different channels. We're working on the cool hip one right now, apparently. I mean, I love Wes Anderson. I think he's great. Tilda Swinton is an amazing actor, but we definitely have the advantage for young hip model to work on. So in detail, basically, if you think there are things in AGN disks, and there are plenty of good reasons to expect that, those things they feel the gas disk around them, they experience torques, and they change their semi-major axis. So they migrate. As they migrate, they find each other. As they find each other, they can form binaries, as Chris mentioned. And so what can happen is things merge and produce gravitational waves. The population of mergers that result can tell you things about the AGN gas disk itself. So this is a wonderful way of kind of reverse engineering AGN gas disks that we've been studying in the electromagnetic bands for probably 80 years now, and they're still fairly poorly constrained. So using the population of compact object mergers that should come from these disks, we can actually probe the properties of the midplanes of these objects, stuff we can't actually visually see. So we can use these things to figure out AGN. Potentially, there are some interesting EM signals that we can also use to figure out properties as well. So in terms of what we actually do, if you want to come and talk to us, we do hydrodynamic simulations, M-body, Monte Carlo. We think about observations of large samples of AGN and interpreting those. We do semi-analytic work. So whatever you're into, we're also into. Stuff we're thinking about right now, we're very interested in the role of both feedback from embedded objects onto the surrounding gas in the disk and what that does to the process of things moving through the disk. Also observational signatures and the impact that has on mergers. We're also very interested in the sort of unique observational signatures in both EM and GW of these things in disks, and what we can figure out from large samples from LIGO and large AGN surveys. So come and talk to us. Thank you.
Okay. Thanks, Barry. We have time for a couple questions. Can I ask you a quick question? So for this kind of black holes formed in the AGN disks, is there very specific prediction about what their spin would be like?
So I had 4 minutes for this spiel, right? How much time do I have?
Yeah, maybe like.
Yeah. So spin is another thing that we're worrying about. So there's a fascinating anti-correlation that Tom Callister from CCA has discovered in the LIGO data, where the effective spin that LIGO measures, chi-effective, increases with increasing mass ratio in binary black hole mergers. This is a really curious, interesting result. And so far, the only celebrity actor director that can explain it is Timothy Chalamet. So potentially AGN disks are a way of generating what we're seeing in terms of spin and mass ratio of mergers. So I encourage other channels, I encourage Tilda Swinton and Bill Murray and so on to try and come up with an explanation for this.
Cool. Yeah, that's really cool. Any other questions? Kiara.
How many of the LIGO events do you think could come through the AGN channel?
So, you know, honestly, it doesn't matter. And the reason genuinely, right? Because if all of the events come from AGN, then we can reverse engineer AGN really, really well. That's great. If none of them come from AGN, that's also really useful because they should happen in AGN. And the fact that we're not seeing any also tells you something about AGN and nuclear star clusters. So like, whatever, you know, like just give me a number and we can tell you something about AGN and nuclear star clusters. Off the top of my head, anywhere between 25% and 80% would be a reasonable sort of fraction. The other thing I'll say is if you're interested in gravitational waves, AGN are also the only place where you will generate sources in LIGO, LISA, and PTA, right? So there's potential for amazing crosstalk between all the gravitational wave regimes to probe these things. So it's very exciting future.
Cool. Yeah, that's great. So let's thank Barry again. Okay, our next speaker is Tyler.
Thank you all for having me here. So I am Tyler Pritchard. I'm a postdoc working at NYU with Mariam Modaz. And she was initially, this pointer really is terrible. Got it. Yeah, so Mary was originally supposed to be here, but had to cancel, unfortunately. So I'm here in her stead, here to give you some teasers about the various work that's going on in our group and encourage you to chat with the relevant person if you're interested, or I can give you a little bit more info later on. But spoiler alerts, we're all kind of interested in how the variety of stellar explosions that we see relate back to the actual stars that explode. And we investigate that in sort of a variety of different ways. And so Mariam, as the aegis who we all sort of work under, there we go, is a faculty at NYU, and she's historically been very interested in strip envelope supernova and supernova GRBs, and understanding how, you know, host galaxy properties of the galaxies that these stars explode in feed back into the stars that actually explode and the explosions that we see. Janelle is a first-year grad student with us who has started up a really interesting project, and she's working with Mariam as well as Dave Russell at NYU Abu Dhabi, who knows him. And the question that they really have actually is, can we constrain the explosions that may have produced the black holes that are in like Milky Way black hole binaries by looking at the metallicities from the stars in the black hole binaries in the Milky Way and comparing them with the metallicities of stellar explosions, basically supernova GRBs, as well as some other potential strip envelope supernova that we know create black holes extragalactically. And so can we combine these sort of two streams of information to really understand the explosion channel progenitor method for these? Mark Williams is a fifth-year graduate student who's been working with us. He has a couple of different projects that are going on. He's a little bit more on the modeling and data science side. So one of his most recent results recently, which is quite interesting, is there's stripped envelope supernova, which are coming from stars that have lost a lot of their envelope. This could be hydrogen, this could be helium, this could be both. And the question is there's always been this idea that we know that they've lost almost all their hydrogen because it's really easy to see hydrogen in stellar explosions. But we don't actually know what could be remaining. So he's been working with TARDIS, rad hydro code, to basically model supernova and then add incremental amounts of hydrogen to see how much you can really bury in some of these explosions. And the answer here is really not a lot at all. So less than 0.01 solar masses of helium, or sorry, hydrogen and helium in this one would show up. And he's done this for 94I, Q1 in particular, and is looking at expanding this. The other sort of more data science thing he's been doing recently is actually taking this rad hydro code and working on machine learning emulators to basically make fitting and error bars for supernova spectral model fits possible. So speeding these up fast so you can basically run lots of models really quickly and understand the actual parameters with error bars that would give you reproducible spectra. And he's been doing a lot of open source software work as a part of that. He also has some interesting physically interpretable supernova stuff that you should ask him about offline if you're interested in classification. But that's a lot of supernova specific stuff, so we're going to sort of skip that. Finally, it's me. I'm a postdoc with Miriam, and I, generally speaking, am interested in finding and studying sort of weird events and thinking about different ways we can use data analysis to discover them. So recently I've been working on finding and studying things that are called fast blue optical transients in a variety of surveys. I don't expect any of you to know what those mean, but as it kind of sounds like, they're fast, so they evolve quite quickly. They're blue, so there's some sort of blue high energy spectra or more emission coming out at lower wavelengths, and they're transient, so they're there sometimes and not most of the time. And I think these days we didn't know what used to cause them, but we're pretty sure now that they're kind of supernova with bonus physics. So you got some sort of nickel-powered supernova end-of-life star explosion going on with some extra source of energy injection that's causing it to be both fast and blue. Fun stuff. In particular, we were studying one right now where we managed to get early test data on it. So TESS is actually an exoplanet satellite, but it stares at one point in the sky for a very long time. And occasionally you get really lucky and a supernova goes off in there, or less than occasionally because it actually has quite a wide field of view. But the cool thing about this one is with this really early time data, we actually see it sort of turn on. And the way that that turns on in this sort of shallow turn is indicative of that's probably either exploding through a very puffy envelope or interacting with some sort of mass loss right before the supernova happened. So at least for this one, the bonus physics is probably like CSM interaction kind of thing. But the other cool thing that we've seen with these is that while they are supernova with bonus physics that are weird, they're actually much weirder in like the UV and in some ways the near IR than necessarily the optical. So we recently got some money to actually create a multi-wavelength transient archive, not for just FBOTs, but for all transients that we can kind of find to get as much basically UV plus optical data and throw in some near IR where it's available. So we have as much like of a flux complete kind of archive as possible. And this is super important for me because I want to find weird things. You need to know what's not weird to be able to do that. But also from a supernova identification classification side, most of the work that's been going on to date is using things like model training sets like Plastic or others to run your machine learning models on, and these can be used to create data-driven training sets as well as like model parameters so you can do physical outliers and other fun things. Thanks.
Thanks. Maybe a quick question if anyone has. I think we have to move on, so let's thank Tyler again. Okay, our next speaker is Naveen.
Good afternoon, everyone. I'm Naveen. I'm a fourth-year grad student at Columbia, working with Brian Metzger, Lorenzo Cironi, Andre Belabero, and stuff. So fast radio bursts are millisecond duration extragalactic events of radio pulses. One FRB has even been discovered from our own galaxy, and the emission mechanism behind fast radio bursts still remains a mystery. These are extremely bright events, and their brightness temperatures can be of the order of around 10 to the 35 plus Kelvin, which demands these sources to be coherent demands some coherent emission mechanism to be operating behind these sources. Some FRB sources are repeaters, whereas some others are one-off sources. So they just emit once and then they disappear. And among these repeating sources, some have been found to be periodic. And if you're interested in the periodic repeaters, come talk with me. We have some ideas to share. I'd be happy to talk about that. Recently, the Canadian chime, the chime instrument, which is the workhorse of FRB discovery, they put out their first catalog containing more than 500 FRBs. And this catalog revealed a very interesting dichotomy in FRBs. That is that. So yeah. So this is the sample of the chime FRBs. Here you see the one-off events, and in the right panel you see the repeater bursts. Interestingly, the one-off events are narrower in width compared to the repeaters, and they are typically broadband compared to the repeaters. So the repeaters are wide in duration, and they are narrow in their spectral widths, and compared to the one-offs. And we do not really know why that is, because repeaters and non-repeaters are expected to be coming from same dispersion measured in some same distances. So here's an example of those bursts. To the left, I show a non-repeater. You can see that these non-repeaters are very short duration, and the right panel here shows their spectrum. It's a power law-ish kind of a spectrum. And to the right, you see a repeater. You can clearly see a very distinct difference in their burst profiles. It's wider, and their spectrum is Gaussian, kind of Gaussian. And they also drift from higher frequency to lower frequency. So we have come up with a very simplistic phenomenological toy model to explain this particular dichotomy that's seen between repeaters and non-repeaters. So we consider FRBs as narrowly peaked pulses whose peak frequency drift and the luminosity scale as power loss with respect to a singular point in time. This initial time can be say when the initial flare happens, for example. And we define the central frequency, nu c, going as some t to the power law index beta. The burst, so the central frequency is basically, okay, this sometimes does not work. Okay. The central frequency is, for example, at t equals 5 seconds, the central frequency is 600 megahertz. And then the instantaneous burst bandwidth goes as the central frequency, it's proportional to the central frequency. With these two, you can figure out what the burst drift rate is, just take a time derivative of this, and the burst duration of the FRB would be the burst bandwidth times the burst drift rate. So this is what the very simplistic phenomenological model is. It basically says that the central frequency drifts as a power law with time, and so the flux of the FRB. So with this, we simulate some FRBs. So these are all not real FRBs; these are computer simulated ones for different power law indices beta. Remember, these power law indices beta determine the central frequency drift rate with respect to time. And you see that for larger beta over here, the duration of the burst gets shorter, and the signal to noise ratio, which I've shown in the left panel here, it is accumulated pretty much across the entire bandwidth of the instrument. compared to smaller beta, where the signal to noise ratio is accumulated at one particular narrow strip of the bandwidth. So the spectrum for small beta bursts will also be very narrow. It's kind of a Gaussianish compared to the spectrum for large beta bursts, which would be power law kind because they are spread throughout the band. This suggests that repeaters must prefer smaller power law index beta, whereas non-repeaters may prefer larger beta. So physically, as up until now, this toy model is agnostic of the engine that is powering the FRB. There are two major models of FRB production. One can be shock ramming onto the upstream medium. Synchrotron major instability can happen and produce FRBs. The other popular model is FRBs are produced by charged bunches traveling along the magnetospheres of magnetars. So this toy model is agnostic of that. So this beta can be related to, say, in the synchrotron maser shock models, it can be related to the density gradient of the upstream medium. And changes in the density gradient can change beta and therefore can give rise to this dichotomy. And this beta can be related to somehow radius to frequency mapping in magnetar magnetospheres. I think that's it. I will stop here and take any questions if there are.
Thanks, Navi. Any questions?
I'm a little hung up on the physicality of the middle. So I should back up for 1 second. I got my PhD on the Chime FRB team. So I'm a little hung up on the physicality of that central beta equals 5 or beta equals 0.5 plot. I'm not sure I've ever actually seen an FRB in the wild where it's very sharp at the top of the band and then the downward drifting frequency structure like shrinks in size as it drifts. Do you have a particular motivation for that? Because that's not. Yeah. I would say that doesn't look the same to me as the other one. It stresses me because.
Which one?
So what is weird to me, I think about the beta equals 0.5. So that's a broadband burst with this tail off.
This is somewhere in between. So the Chime started using a spectral rolling index, not necessarily, which is different from a spectral index now, which takes care of a Gaussianish and power law, which convolves these two parameters somehow. So this is in between a power law index and.
It worries me a little bit that I've probably looked at more FRBs than most people in the room, and I've never seen one that looks quite like that. So I'm wondering if there's really a continuum or if there's two sets.
That's a good point. It may not really be a continuum. This is just an in silico FRB. Just to show that by changing the beta value from one extreme to another extreme, you can produce this dichotomy. Maybe the nature does not like beta of 0.5, and repeaters are from 0.1, and non-repeaters are from 1. That's possible too.
Yeah, I mean, it's an interesting thing to try. I'm just a little nervous that I don't see many that look like that IRL.
Yeah, I'm happy to talk about it. It's a zoo of FRBs there.
Yeah, I think we have to move on so the discussion can give to the coffee break. Let's thank Navin again. Okay, the next talk is me. So, I'm giving the final talk for this session. Okay, hello everyone. So my name is Yajie Yuan. I'm a postdoc at CCA. I work on various things about high energy processes around black holes and neutron stars. Today, I'm going to talk in particular about our model for a particular scenario for fast radio bursts from magnetars. As Navin already mentioned, so fast radio bursts are mysterious millisecond duration bright radio bursts from cosmological distances. So we still don't know what produced these fast radio bursts. Last year, there was an important discovery that the fast radio bursts were detected from a galactic magnetar, this object called SGR 1935-2154. So this is the detected fast radio bursts. There are two bursts separated by 30 milliseconds. And very interestingly, concurrent with these fast radio bursts, there was a X-ray burst from this magnetar. So this is basically the light curve of this X-ray burst. And you can see these two peaks in the X-ray burst correspond to the two peaks of the fast radio bursts. So this discovery tells us that maybe indeed magnetars can produce some of the fast radio bursts. And this may well be related to a process that also produced the X-ray burst from the magnetar. So we have been thinking about a possible scenario to produce this kind of bursts. So what we think is that for this kind of magnetar bursts, it's usually triggered by a star quake, where basically the disturbance on the stellar surface breaks the crust, maybe due to the internal evolution of the magnetic field. So the crust will shake under the star quake, and that will shake the magnetic field lines anchored on this region. So if we shake this region, there will be plasma waves launched along these magnetic field lines. So these are basically orphan waves. They are just like elastic waves when you pluck a string. So these waves will go out along the magnetic field lines to large distances. So the interesting about these orphan waves is that they carry energy, and they can carry energy to large distances. We find that, for example, the orphan wave here, it can move along the magnetic field lines and then become nonlinear at some points. And this becomes an ejecta that contains a lot of energy that moves out from the magnetosphere of this magnetar. So basically this nonlinear breakout of this orphan wave launches an ejecta into the magnetar wind. So as the ejecta moves out into the surrounding media of the magnetar, it can launch shocks. So we can also look at this in full 3D. So this is another simulation we did to look at a localized star quake on the stellar surface that launch orphan waves. In 3D, you can also see that the orphan wave can become nonlinear and break out and launch an ejecta there. Although this disturbance is only launched from the small region, it can still open up the whole magnetosphere and basically launch an ejecta into the magnetar wind. So, and in this case, the energy distribution in this ejecta is actually relatively compact. It's not larger than angular size of like 0.5 stellar radian. Okay, so this kind of ejecta launch from the magnetars can basically produce shocks at large distances. And as we know, there's a mechanism called the synchrotron maser at the shock fronts that can produce the radio emission. And also we think that in this ejecta process, there can be this current sheet where a lot of magnetic reconnection happens. You can see this kind of small structure here. These are plasmoids generated due to the reconnection. So this dissipation process can actually produce these X-ray spikes that we think is probably the origin of these X-ray spikes seen in the X-ray burst. So we think this is possibly a scenario for these fast radio bursts from the galactic magnetar. Okay, I will end here. I think we are almost running out of time, but if you have questions, feel free to talk to me after the session. Okay, thank you, everyone.